All right, thanks everyone for coming. Just some starting. Looks like we're filling up pretty good. Please pack in, and also please turn your cell phones off for the start. At the end, there's a survey, of course, and it'd be great to get some feedback from you. Just quality of content, what would you like to hear more in the future? So that said, let's get started. I'm Max McMullen. I'm the development lead for Direct30 at Microsoft. My team engineers and designs the Direct3012 API. So just super happy to be here today, talk about what's changed in the API since we last talked, and give you some new insights into how the Direct3012 API can make you build new, more powerful, more rich games. So the bulk of the talk is going to be developer-focused in terms of the API surface, but I'm going to take a little bigger picture to start with. Let's talk about the platform, which is Direct3012 on top of Windows 10. So it's been an incredibly busy year. We first announced a year ago at JDC 14, and that was a great announcement. We saw a lot of good response to that. The API at this point is largely complete. There may be some small tweaks based on feedback from our early access program still to happen, but in general, the API is today what we expect to ship later this year. Great news is we have fully functioning and very performant drivers across all three main PC hardware vendors. And during the talk today, you'll see demos on each single driver in some performance scenario. So you'll see an Intel driver running, you'll see an AMD driver running, you'll see an NVIDIA driver running. Second really cool thing since last year, when we first started talking about Direct3012, we ended up designing to try and hit a large quantity of hardware, which is something we haven't really done before. Usually we design D3D to be a little forward-looking, and it picks up some coverage as we go. This time, last year, we said Direct3012 is going to reach 50% of gamers when we launch in terms of hardware coverage. We're actually already at 50%. We were a little conservative last year, just intentionally. We don't want to set expectations wrong. We're at 50% today for hardware based on the Steam survey, and we expect holiday this year, we're actually going to be at 2/3 hardware coverage. So it's going to be a great, huge platform with lots of endpoints to reach in terms of selling your games. Next point, we've seen a huge amount of industry adoption and success. We already have the Unreal Engine 4 ported running in performant ways. We have the Unity engine, which was announced to support it, and later during this talk, you'll hear from one of the Unity graphics engineers about their porting effort. In terms of tools and infrastructure, there are talks later this week where you can see how the new graphics debugging tools from Microsoft enable you to build 12 games faster with more conformance and accuracy. In terms of early access, we have over 400 members on our early access program and forums with questions and answers flying daily. That represents over 100 studios. So we also have games. AAA titles already announced. Fable Legends is already announced to be on top of Direct3012. And also Ashes of the Singularity from Oxide Games is announced to be Direct3012 as well. Finally, a year ago, we couldn't really fully answer where Direct3012 was going to be. It was just too early in our planning. But as you've heard, Direct3012 is a Windows 10 exclusive. That said, Windows 10 is free for every Windows 7, Windows 8 customer for a year. Effectively, we've taken the DirectX redist model, where you used to be able to install new versions of DirectX and old OSs, and flipped it around. The redist is everyone gets a copy of the OS. So that's the platform. We think it's a really great story. You'll be able to reach lots of customers in the end. Let's dive down a little bit and talk about the API and what it can provide you, the developer. So the agenda is roughly 3 parts. I have some teasers on here as well. The first part of the talk, I'm going to do a brief refresh just on all the Direct3012 concepts that have been introduced the last year. Some of the later discussion about CPU and GPU performance features that are not announced will build off of that earlier content. The middle section is going to be Casper Engelstoft from Unity talking about how their porting effort went, moving on to Direct3012. And the last section, I'm going to talk about new API features that haven't been announced before and how you can get greater CPU performance and even greater GPU performance, a story we haven't told before. Last, I have a really awesome comparison where we can show what you can do with Direct3012, showing Fable Legends 11 versus 12. So let's get started on the refresh. The main points of D312 that we've been talking about for last year: dramatically reduce CPU overhead and greatly increase scalability across CPU cores, ultimately resulting in vastly greater developer control over how your rendered content can be realized on Direct3D. effectively, we're going to give you console-level efficiency and performance and even control on the PC platform. We're going to give you greater performance and access on the console, and for the first time, we'll have that level of performance also on mobile. Finally, we've done all this without reducing any rendering functionality. You can do anything you can do on 11, you can do on 12. So let's just recap the CPU overhead multithreading improvements. There are a bunch of main concepts, areas where we changed Direct3D from 11 to 12 that enabled those CPU performance enhancements, both in overhead and scaling. At a high level, we've added pipeline state objects. We've created an explicit resource binding model, flexible pipeline parameterization, explicit CPU-GPU synchronization, and last, we've implemented command reuse. So each one in brief. Pipeline state objects, 11 had more coarse-grained parameterization of the pipeline than 9 did, but it still had several objects. And what ended up happening was drivers would compile those together at runtime during draw calls, resulting in CPU overhead. It was just necessary for drivers to actually map those API objects to the actual hardware state that needed to be programmed. Doing a bunch of analysis, we found that really we should be combining all these objects into one big pipeline state object, where it's actually much more trivial for the driver to program the hardware. You can take the one compiled pipeline state and then copy the commands to program all of the pieces of hardware state in one go. Second, explicit resource binding management. So in Directory 11, we had basically, it seemed like a busy API in terms of you're creating lots of view objects, you're creating shader resource views, you're creating constant buffer views, render target views. And for the vast number of resources, usually the shader resource views, that was a lot of overhead, both just in using the API, but also in the internals. We did reference counting, lifetime management, both at the API object level, and also tracking the usage of those resources in actual hardware commands. With 12, we've gone to a sort of an explicit memory model, where those bindings aren't COM objects, it's just structures stored in GPU memory. It's abstracted, so you don't need to know each hardware vendor's layout, but you can treat it like just a struct that can be copied around. You can create a descriptor in a piece of GPU memory. You can copy it from one location to the other. And we group them all together, all those descriptors, into what we call a descriptor heap. It's a large array of these descriptors that you can index and move around as you choose in the shader code. Last, it was really necessary to expose an API concept for representing that range of descriptors you could index around, and that's what descriptor tables are. GPUs have really advanced the last 5 years in terms of how they can bind resources, how you associate a piece of data with the shader pipeline. And it's represented in the tiering we have in the API. We have 3 tiers, tier 1 through tier 3. Tier 1 effectively represents all the first-gen 11 hardware. You'll see a lot of the numbers there in that column sort of match to numbers you've seen in the 11 API. You can have 128 shader resource views at once. You can have 14 constant buffer views. You have 8 UAVs for compute. But as the hardware progressed, we got increasing capabilities. So, we first transitioned to bindless, pure bindless around tier 2. You get a huge amount of value being able to index, 1 million different shader resource views. That's a really, really powerful change where you can start pre-baking all of your resource bindings in the descriptor heap and then just move around it in the shader code. Further, tier 3 actually increases the size of the descriptor heap in case you really have a high-end app that's using a lot of descriptors, but also it makes all the other types effectively unlimited as well. You're just bound by memory at that point in tier 3. In terms of looking at the hardware out in the market right now, again, this is based off of the February 15 Steam survey. These 3 tiers roughly bake out into about 39% tier 1, 44% tier 2, and 17% tier 3. So if you're hitting titles in the next couple of years, you should really be thinking about your rendering in terms of running on both tier 1, tier 2, and tier 3. What goes along with this explicit resource binding model is your application is expected to handle hazards. Hazards are effectively any time work needs to be performed by the GPU to maintain the coherence of your data. So if you have to synchronize or transform the data to move from something being a render target to being a texture, the barrier API allows the GPU to perform that operation. So the classic example is the render target to texture transition, where most GPUs, you need to flush out all writes before you can consume that render target as an input texture. Other examples that are on the slide, copy source to destination. If you're moving data around, you need to make sure the writes are all resolved at some point. There are others, and I'm actually going to talk about a really important barrier later in the talk, in the third part of the talk, that gives you a lot of GPU performance. Flexible pipeline parameterization. This is really, one of, I feel, the awesome parts of the D312 API. We spent a lot of time designing this, trying to build a parameterization of the shader pipeline that was extremely fast, both in CPU and GPU, really flexible for you, the game developer, to fully exploit the GPU. And I don't know, it's, I think, one of the real gems of the API design. We've abstracted parameterization a bit so you can specify constants and pointers, effectively descriptors, that you want to change literally from one draw to the next, really high frequency. And the abstraction allows the driver and the hardware to use specialized fast paths like registers and other fast renaming mechanisms to pass those parameters to the pipeline. You can really think of this flexible pipeline parameterization as a function call for the shader pipe. You have a list of arguments that are integers, floats, pointers, and those get passed to the whole shader pipe. Explicit CPU and GPU synchronization. So, past APIs, if you deleted a resource, we'd guarantee at the API that we wouldn't actually delete the video memory until all your rendering commands were actually executed by the GPU. And that required a lot of overhead, again, in terms of reference counting and maintaining a lifetime. What we have now is, you, the engine developer, really know when resources need to be deleted. You know which frames are in flight, which frames are complete. So we shouldn't have to do tracking in the runtime on a really fine-grained basis from one resource to the next about when it was used. You can just synchronize, with the GPU loosely, and then delete resources once you know they're not being used anymore. Our recommendation is, one fence value per frame they have to synchronize against. Good examples of using this, like let's say you're streaming constant buffers or geometry from the CPU to the GPU. You can just allocate a large chunk of memory that's both CPU and GPU accessible. You write geometry into the buffer, you use it in rendering calls, then you track when those rendering calls are complete on the GPU. Once they're complete, you can reuse the memory for anything else you want. Okay, so this is the first bit of content that hasn't been talked about before. Last fall, around September, I revealed some of the new rendering pipeline features in Direct3D12. They're also available in Direct3D11.3 as well. Features are conservative rasterization, rasterizer order views, typed UAV loads, tiled resources tier 3 for sparse volumes, and one thing we haven't talked about yet is the pixel shader specified stencil ref. So these are incredibly powerful and useful new parameters in the rendering pipeline, or capabilities in the rendering pipeline. Conservative rasterization, you can do occlusion detection, occlusion culling, hit testing. You can do curve rendering. With ROVs, classic example is order-independent transparency. With typed UAV loads, it's really just a very general, powerful feature. You used to hear about people trying to do shader code to munge data into an R32. That was our only main format in compute for a while. Now you can just use an R8, G8, B8, A8 if you want for storing data and have it read properly. You don't burn extra shader instructions. Last, tiled resource tier 3 with volumes, like sparse volumes. There's a huge amount you can build with sparse volumes. Global elimination is one, but there are many other useful algorithms that can be built off of sparse volumes. Pixel shader specified stencil ref, it's a relatively small tweak to the pipeline, but again, it's pretty useful. You can actually specify the stencil ref value inside the pixel shader. So what we didn't announce last fall, we actually have new feature levels, and we've grouped them together. You can see that we have feature level 12, which is resource binding tier 2, tiled resources tier 2, and typed UAV tier 1. Really, 12.0 is a transition into the bindless model. It's incredibly powerful, and it gets a lot of CPU advantages, performance advantages that 12 provides. Pre-bake your binding, large worlds, track material indices throughout your pipeline, and just index the descriptors. There's no binding left necessary. Typed UAV tier 1 actually is better associated with the feature level 12.1 features, but the reality is most GPUs, in fact all GPUs out there that are 12.0, quite wide variety of 12 hardware already supports this, so we put it earlier in the feature level list. Feature level 12.1 are just some really general, incredibly powerful rendering pipeline features, as I mentioned before. You can build a lot of interesting algorithms off of conservative rasterization and ROVs, and in fact the two of them work together in very interesting ways to enable new rendering algorithms. So those are the rendering features in Direct3D 12, and that was the background and the refresh of all the talks in the last year. It was a bit fast, I know, but if you want to see more, I'll have a slide at the end. It'll show you the old talks you can watch. There was a talk at IDF in September. There was the talk actually at last year's GDC as well. And I'll walk you through each of those features in more detail in those talks. I'd like to invite Casper Ingolstadt up from Unity. He's going to talk a bit about his experience porting to Direct3D 12 in the Unity engine.
Thank you, Max. So we've been working closely with Microsoft and the hardware vendors to bring Direct3D 12 support to Unity. And today, I would like to talk a bit about our experience porting, and then I'll talk a bit about how we got some pretty nice gains from both from multi-threading and from using Direct3D 12 when doing shadow rendering. And last, I'm going to look a bit ahead and try and talk about where we're heading for the future with Direct3D 12. And we started in September last year with the SDK1, which came out already in March, and it had some early drivers. So it took about 2 weeks for us to get to know the API and get something rendering inside Unity. It wasn't fast, but it was rendering. And we had the fortunate experience of our shader pipeline already generating correct bytecode for shader model 5.0. So we had a lot of progress really quickly because of that. So in October, SDK version 2 came out, and there was some fallout from that because of when you work with pre-release SDKs, things change, things get optimized, some concepts getting rearranged, and it's all for the better because you have a chance to mold the API a bit into something that works better in real life. But it also means it's more work because you have to refactor some code. But from October to December, we spent the majority of the time getting our graphics tests passing, and we have this big framework of test scenes that we try and render, and then we compare them to some reference images. So it can be special cases from our customers' projects, or it can be synthetic scenes where we just test one specific thing. So we ran this on the X12, and we could see exactly what was working and what wasn't. So we went in and fixed each individual thing one at a time. And we actually spent the majority of the time during this period dealing with various driver issues because of very early drivers. And our life would have been easier if we have had a functional graphics debugger at the time. It is getting improved and will be available pretty soon, I think. So I hope you guys will have an easier ride. So by mid-January, we had 95% of our internal tests passing. And then SDK 3 came out. So some of the new concepts that got introduced were not that great for our performance. But it's because we tried to do a straight port. You shouldn't expect to have the same kind of performance when you just do a straight port because of the new resource binding concepts and how you do synchronization. So you actually have to take a step back and rework your code for performance. But then you also have the ability to get some really nice gains once you leverage the API. So we had to rewrite our dynamic VBO implementation. As you might know, there's nothing called map for discard anymore. So instead of doing like we used to on 11, we allocate 1 megabyte chunks, and then we have our dynamic VBOs grab into that buffer using a view. And as Max said, when the GPU is done and you know that you won't be referencing the memory anymore, then you can reuse it later. So the first thing that we looked at for performance improvements was the multi-threading of shadow map rendering. It's something you can do on your existing engine, and you can get some nice gains from it, both because of multi-threading, but also because of the way D3D12 works. So the main goal is to move work away from the main thread. Many games are main thread bound, and we can do something about this by moving expensive things like shadow maps away. So D3D12 is forcing us to change the way we think about both generating rendering commands and handling resources. So that forces us to do things that can give us a performance boost later on. So in Unity, we have the concept of a master and a client graphics device. So we generate a command list that is then converted to actual API calls on the client device. But on D312, we can actually generate rendering command lists from multiple threads. So we can skip this intermediate command list and directly generate the D3D command list, which is an improvement because we don't have to go through this intermediate step. So the main thread builds the main scene command list, while the worker threads are generating the shadow command lists. Then by the end of the frame, we will do the synchronization, execute all these shadow map command lists that has been generated asynchronously, and then the main scene command list at the end. And this is nice because we completely decouple it from the main scene, and it's a fairly simple render loop because you just set a render target, set a little state. Each draw call doesn't do a lot of stuff because it's just shadows. And then in the end, you end up in a place where you don't have the extraction of shadow casters and shadow receivers on the main thread because that's fairly CPU intensive. It's something you don't want to do on your main thread where you ideally want to do game logic and other things just controlling jobs execution. And this is our results. This is before. This is a synthetic scene where we, okay, no laser pointer then. So as you can see, the render shadow map calls, we have 3 of these, are inlined on the main thread. And it's a synthetic scene of 7,000 objects getting lit by 3 directional lights, casting shadows. So there's a fair amount of work going on in the shadow map functions. And it takes about 23 milliseconds for this scene. And it's all in this one function, render shadow maps. And it's something that had to be done on the main thread because we had this, we had the function referencing a lot of global state. And on D312, you have the immediate context. And on 12, you don't, which forces us to think a bit out of the box. If we want to move stuff to other threads, you have to not reference global state. So we had to rework our materials. We had to rework the way we deal with meshes. And every time we reference something, you actually have to copy it out. So we generate this chunk of memory that we can pass on to the job, which then have read-only access to a copy of the data that doesn't. That's basically immutable. And this is after. So as you can see, the render shadow map functions have been moved to some worker threads, and frame time is down to about 13 milliseconds. So we got a gain of 10 milliseconds just by moving this away. So a really nice boost that so you can use your frame time for something else, like generating even better games. And prepare shadow maps still runs on the main thread. This is where we do the extraction of what needs to be done, and calculate memory requirements for render targets. We do calculating bounds, shadow cascade parameters, and we find out what needs to be done on the job. Then we execute the job, and once we're done with the job and the synchronization, we can kick off these command lists in the end. So looking forward from where we are now, we would like to first be feature complete, of course. And then later on, we will look into some additional optimizations that is made possible by the advanced features in Direct3D12. First thing is the pre-recorded command bundles. Command bundles lets you do things faster. You can issue more draw calls because each draw call will be cheaper. And it's something that you could either do for perhaps for your shadow map rendering or for the new reflection probes that we have in Unity 5. We do a lot of GPU-based convolution and generating mid-levels for those. And all that can be recorded into command bundles, and you can execute those with very little CPU overhead. There are also some features in Shader Model 5.1 that we would like to leverage, the descriptor tables. When your renderer can access thousands or even millions of resources in the shader directly, then you can move even more work away from the CPU and onto the GPU. So the GPU can do the fetching of resources instead of using a lot of CPU time putting things in the right containers. You can just index and read everything from the GPU. So that's something that we plan to leverage for our deferred renderer. And that's all I have for now. And I'd like to see Max on stage again. Thank you, Max.
Thank you, Casper. OK. This I actually think is the fun part of my portion of the talk. So we've told a story for the last year about how we have greatly reduced CPU overhead and dramatically improved scalability across cores. The part we haven't told you much about, but is still really awesome, is we have GPU performance improvements as well. And so I'm really happy I can reveal all this to you today. I'll get to the GPU performance improvements in just 1 second, because we do have one CPU improvement we didn't talk about. So we've actually had this in the API design for a while, but I wasn't ready to talk about before. We think at this point we've got enough gains, and it's a positive experience. We're going to ship it in the API. We actually have a developer-controlled shader cache in D3012. So if you look at 11 games, typically you'd see huge stalls at application startup, huge stalls at level load. And then if you had dynamic shader compile cases, you'd see glitches as your engine ran into a new combination of shaders that just hadn't been there before. So PSOs actually had the possibility to make this worse. You're doing a lot more heavier weight compiles where you're combining a lot of shader stages together. We're actually going to see hardware vendors doing a lot deeper analysis, looking across the pipeline stages, trying to eliminate shader code that didn't actually have to be there. So with even heavier weight shader compile, it's even more important to be able to cache the results. So what 12 has, 12, we see 200 to 400 pipeline state objects per frame, and if you look at a longer trace, the combined set of unique pipeline states looks more like 300 to 1,000. The cache in D312 is developer controlled. When you create a PSO, you can specify a flag saying you want to cache the output. You create the PSO, and then we'll give on the out on the API a binary blob representing the almost fully compiled hardware instructions themselves. I say almost because, of course, it's like a DLL. You have to repatch, adjust addresses, things like that. But in general, all the heavyweight, really expensive compilation operations should have been done at that point. Last, it's not an OS cache. We're not managing the storage for you. We're just giving you the developer control over which PSOs you want to cache, where you want to store them, how much disk storage you want to allocate to storing those cached objects. It's really, there's such a wide variability, we think it's better under a developer control. Certainly in the OS, this is meant as a primitive, and we'll take advantage of this for other scenarios. But the API is meant to give you control, and that's exactly what the cache provides. This is one of my favorite API features, actually. So if you look at my talk a year ago, the talk a year ago, I was presenting bundles, how we have these pre-recorded chunks of commands. And don't get me wrong, those are actually extremely valuable. As developers start using 12 more and more, you'll actually become command processor limited. There's a small processor on the GPU that consumes all these rendering commands and then makes all the shader cores and the fixed function hardware execute in the right harmony to produce your rendered results. And 12, you can actually completely overwhelm that command processor sometimes. And bundles are really nice. They get the optimal sequencing of command processor commands. That said, there's a debate in the last few years about multi-draw indirect, where a lot of developers, and even I could see this, it's really powerful being able to generate draw calls and dispatch calls on the GPU to be able to generate parameters that you set for those calls. And we knew it. We really wanted to expose it, but when we looked across the hardware and worked with the hardware vendors, initially it didn't really seem possible, so we built bundles trying to get part of the way there. Well, in the time between last year and this year, we've made further progress in designing them, and we actually have a complete indirect dispatch and draw solution that runs on all 12 hardware. So that's for feature level 11.0 and up, what we have is Executelndirect. It replaces the 11 API concept of draw and direct and dispatch and direct. You can generate multiple draw calls with a single CPU side Executelndirect call. Those Executelndirect calls, they have a developer specified set of parameters. So it's not just about how many draws or dispatches, but that pipeline state binding I talked about earlier, you can actually change constants in it and change descriptor pointers for each draw call by filling out this indirect draw buffer correctly. That indirect draw buffer can be a CPU accessible buffer or it can be purely a GPU accessible buffer. So again, you're in control of how data flows. You can choose to fill out the buffer on the CPU side and stream it in. If you want to have purely GPU generated draw parameters, you can just create it with a compute shader or some other algorithm on the GPU side. So it's incredibly powerful. It's really cool, and we're really glad we could get to this point in the 12.0 API design and get it working on all current GPUs. So as I mentioned, there's a signature. It's very much like the root parameters and root arguments that are used to parameterize the pipeline state object. It just builds on that a little bit. So you can change the vertex buffer, the index buffer as part of the Executelndirect buffer. You can change the roots constants, as I mentioned. You pick for the signature whether that's going to be a draw instance, a draw, or a dispatch call. So it's overall just really, I think, powerful API feature. So you're going to have command lists for streaming dynamic sets of commands. You have bundles for sequences of draw and set PSO. And then last, coming from the other direction, if you have a predictable PSO, you can actually change all the other parameters and stream them in with a single Executelndirect call. So just, this is going to lead into the demo. This gives you a picture. If you have a sequence of rendering calls where you aren't changing the PSO, but you're changing some of those root parameters, issuing a draw, changing more root parameters, issuing a draw, it looks like the loop you see on the left. It's, 12 is pretty fast. Like, it does these operations extremely well, but nothing beats not having the loop. In fact, if you want, you can, if your rendering parameters allow, you can pre-bake the command and reuse it from one frame to the next. And that's exactly what you see on the right. It's just we're setting a root descriptor table, and then we execute indirect on a pre-built indirect draw buffer. So first demo I'm going to show you, this is based off of the Intel Asteroids demo that was shown at SIGGRAPH last year. Andrew Alertson at Intel wrote this. He did a really great job. He was trying to show just how fast D3D12 was without taking any cheating. If you look at the Asteroids demo, you see just lots of asteroids that might blend together, but actually each one is uniquely drawn and uniquely parameterized. He didn't do any instancing tricks there. So what we've done working with Andrew is we modified the code to make one assumption. We said, what if we can assume we had bindless, which means that all the shader resource views could be set up front inside the descriptor table. If you have all the descriptors set up in bindless up front, we can actually represent the entire set of unique asteroid draws with a single Executelndirect call. So let me just start the demo here. Oops. There we go. Thank you, Bennett. Okay, actually, let me restart this. There. Okay. Yeah, so we're running in D3D12 mode. I'll actually pull it back and show you D311 just for a comparison. So here we are running in Direct3D11 mode. We're getting, 28 FPS or so. Then you can see the CPU on the right. We're tracking, looks like about 20% CPU. So this is not in frame rate locked mode, so I'm going to let it free run. It'll run as fast as it can. This is fully utilizing the GPU and CPU as much as 11 can on this Intel Brix Pro. Switching to D312, we get about 3 times the frame rate, but we've only doubled the CPU usage. Furthermore, instead of being serialized on the driver thread, You can see we're breaking the rendering workload across multiple processors at this point. Now, let's make that bindless assumption I mentioned earlier. Sorry, 1 second, I have to switch back to the app. So if we make the assumption that we can pre-bake all the textures used by the asteroids, we get about 80 FPS. So we've just got about a 10% improvement in GPU performance. And if you look, we actually got a few percent decrease in the CPU usage to get that point. Last, let's change all this so it's the exact same rendering, but we're using Executelndirect. We just got another 10% GPU performance, and our CPU utilization dropped down from about 25% to 9%. So this is the exact same demo with the one assumption you can do bindless. We just got you 20% CPU, 20% GPU, and a huge reduction in CPU overhead on top of that. What that looks like here, just in terms of numbers. So one thing to understand, these CPU times are total times across all cores summed together. So you see, we have a steady improvement in CPU time. And if you're wondering why the 12 and 11 are so close, that 11 times 39 milliseconds, that's serial. That's just taking 39 milliseconds and limiting your frame rate. 12, that 33 milliseconds is spread across 8 cores. So your actual serial time is 4 milliseconds. The CPU goes to sleep, and you get all the power moved over to the GPU. So 12 is a huge advantage, actually, over 11. Next, 12 bindless. We already have great performance on 12 at that point, but 12 bindless gets us significantly reduced CPU overhead in sum total. And we get even, we get that 10% GPU performance improvement I talked about. Last, Executelndirect, huge, huge, huge decrease in CPU overhead if you can represent your rendering that way. And again, we get another more than 10% reduction in GPU time to render the exact same frames. So that's Executelndirect. I think it's an amazing, awesome feature in D312, and I'm really glad we could engineer it into all D312 supported GPUs. Let me talk about a little more a smaller feature in the API. We have a flexible predication and query model in 12. So if you used 11, 11 was good for its time. We had API objects representing individual queries and counters and predicates. But more and more modern techniques are using larger and larger quantities of queries and predicates. And it became really unwieldy using individual API objects. And it was a lot of overhead actually checking them and going back and forth between individual predicates and the driver. What we did with 12 is actually we built a memory representation, a video memory representation of predicates and queries. So you can allocate a large chunk of them on the GPU. They start off in a hardware-specific form, and then in that hardware-specific form, you can do rendering operations and predicate and do computation. But also, we give a resolve operation, so you can take those predicates and queries, resolve them to a known buffer format, then use them in your shaders or even on the CPU side at will. So again, we have this model where you can do GPU side operations or CPU side operations, things move back and forth seamlessly because we have a standardized memory representation of the object. If you have lots of occlusion queries or lots of predicates in your rendering, you will see performance increases because now you can do batch operations on those. Those predicates and queries, those tie into the next feature I want to talk about, which is Multiengine. So Direct3D 12, it doesn't have a monolithic queue like 11 did. 11 did do some parallelism and is all left up to drivers to manage it behind the scenes. 12 has an explicit multi-queue model. And we've grouped the different types of queues into basically 3 greater capable tiers. You start off with copy, the ability to sling data around. Copy is going to be really important for discrete GPUs where you want to do background texture streaming, moving things from the CPU to the GPU and back. Compute, next level bigger. Compute gives you all the dispatch functionality that you had in 11 and more. It doesn't have 3D capabilities. The nice property of that is that a lot of modern GPUs have greater preemptibility and schedulability of pure compute workloads. At the same time, those queues and contexts are smaller than the 3D context. 3D is actually rather a large block of state because of all the fixed function hardware that has to be managed and maintained. So if you want to do async compute, this API 12 is designed to extend and support that programming model. as the GPUs get more and more capable. Last, 3D. 3D can do everything. It matches basically what 11 was capable of. So you can see that with this tiering and the prioritization of the queues, we actually enable a lot of scenarios people have been talking about for a while. You can do low-priority background tasks or high-priority latency-sensitive workloads. Our priority mechanism is simple for the 12.0 release, mostly because I think we're intersecting hardware as it's developing and being enhanced. So we have simple low, medium, high type prioritization schemes, and the scheduling logic picks the highest priority task to execute next as long as it's unblocked. In the future, you can expect us to innovate on this prioritization mechanism and possibly expose additional concepts like spatial and or real-time guarantee requirements. But for now, it's low, medium, high. Just to very high level show you what we're talking about, we would expect your game, if it's streaming textures, say, in the background, you'll end up writing code that results in the following patterns. You'll have a background streamer. It's aware of where the player is. It's aware of where you're going in the world. You know roughly what textures and resources you have to stream in. You'll prioritize the most important ones first. So you issue copy operations, allocating memory and moving them in on one thread. Meanwhile, you have a bunch of 3D threads trying to parallelize and render your scene graph. And that's proceeding as planned with all the existing resources it needs. At some point, your render threads will realize, oh, that thing that I streamed, I've got to have that now. Like, it's really got to be there for the frame to render. And so you can actually use synchronization primitives to make sure that the streamed texture actually completed. You have more parameters and controls because the predication mechanisms I talked about actually apply to all the queues. So you can, let's say you put a big streaming operation in and you're like, actually, that's not really valid anymore. I don't need that. You can predicate it away, and that'll let the queue move on to the more important tasks. So in the example you see on screen here, the signal happens if you follow time left to right. The signal happens before the fence, so that fence actually turns into almost a nothing in terms of overhead. There's very little GPU and CPU time spent on that fence. So the 3D queue just proceeds because the streamed texture is already in place. If we were to, say, swap it around just to show you, like, as you expect, a fence operation, if you really depend on something to complete, you can issue a full fence. You don't predicate anything. We'll stall the queue and wait for the stream to complete, and then you continue rendering. Of course, this isn't ideal, but it's just to illustrate the full flexibility of all the synchronization primitives we have in 12. So let me switch and show you the multi-engine demo. So some background on this demo. In D3D, we take conformance very seriously. We build lots of conformance tests trying to ensure you have a consistent experience across all the hardware vendors. I'm actually going to show you one of the scenario conformance tests that we build, and it's just meant to test the overall execution, make sure the scenario works end to end. In this case, the workload's going to be a Mandelbrot render using a compute queue, and in the background, we have a copy queue slinging memory back and forth. And what you'll see is that if we execute the copy and the compute in serial, as you would, say, using just a 3D queue, it'll take much longer than had you actually parallelized and used both a compute queue and a copy queue in parallel with the parallel tasks. I should mention that this is actually running on an NVIDIA machine with an NVIDIA driver. So you can see right here, again, this is a conformance test, thus the wonderful UI. So on the left, you see the average time per frame, actually average workload for the working set. We have 396 milliseconds doing a serial set of compute and copy. On the right-hand side, you see when they're fully executed in parallel, it's about 253 milliseconds. So we're getting great parallelism, and it's really going to enable you to build all these streaming architectures in the background for continuous worlds with no glitches. Okay. Another, I think, really, really cool feature in the API. So UAV barriers. 11, in terms of the hardware spec and how we documented the API behavior, if you have a draw call that uses compute, or if you have a dispatch call, what we expect is that the GPU and the driver must guarantee that all the UAV accesses for a given draw, compute, or dispatch must complete before the next draw, compute, or dispatch. What that means is if you have really small draw computes or dispatches, you end up with lots of idle shader cores. Like, you just have processing power sitting there waiting for you. And so 11 took this approach both for consistency reasons and because 11 had a very correct focused model. 12, we're really trusting the developer to understand how things are parallel and to make the proper choices when to wait for things to complete and when not. So 12, UAV accesses are truly unordered in the sense we've put, UAV is an unordered access view. We've put the U back in UAV with 12. So in 12, UAV accesses are completely parallel. If you have a draw compute and then a dispatch, those will be executing completely in parallel in some cases. And the only time that we enforce ordering is actually when a UAV barrier is emitted. So in most cases, or in many cases actually, the barriers aren't necessary. We can get dramatically improved performance, as I'll show you in a second. Again, from a conceptual point of view, if you look at how things execute, 11 pretty much had this pattern. So some drivers actually on 11 could eliminate the wait for idles, but the way they eliminate them is they're doing analysis on the rendering pipeline state. So they're spending CPU to get GPU perf back. And really, 12 is have cake, eat it too. We don't want the driver spending that CPU overhead. We want all the GPU performance. So you can just emit the barrier when you need, and any excess wait for idles are eliminated automatically because you know as the developer what you need synchronized. So let me show you. Nope. Wrong machine. Maybe we'll have to do a switch. Might be a different output. Technical difficulties. Well, this is both the next demos, so. It got turned off.
It was on when we left it.
Okay, cool. Okay, you might be wondering why is there a debugger up? So this is going to be running, you're going to be seeing Fable Legends running live. The load time in terms of this setup, because we're still experimenting, playing with the engine. The load times are not optimized. We wanted to just do the load time ahead of time and pause it so you can see the demo right away. So let me start it executing. Oh, nope, that's not good. So what I'm going to do is so like I said, this is going to take a while to load. I'm going to try something I haven't done before, which is I'm going to show you the next demo and come back to this. So this is the UAV barrier demo. I'll come back. This is going to show you with and without UAV barriers. Let me do the final kicker first, and I'll go back. So let me. 11 versus 12 on Fable Legends. So I'm going to show you a video. This is actually running live, I believe, in the demo booth, so you can go down and see it down in the expo hall. This video has been edited so you can see 11 and 12 running simultaneously. 11, you'll notice, 11 will be on the bottom. the window will be smaller. The reason it's smaller is that 12 has up to 20% increased GPU performance. So we get greater resolution on 12, which will be on the top. 12 will be running 1080p. The bottom will be running about 900p. And they'll both be running equal frame rate, where 12 is just ever so slightly faster. Yeah, so this is the other demo, which is loading. So you can see the frame rates are approximately equal. 12 is on top. It's actually running a little faster. GPU time is about the same. And we're getting equal perf with 12 rendering a much higher res screen. That's due to UAV barriers and some other performance optimizations that Bennett Sorbo in his 12 talk on Friday will actually go into more detail. I'll need to drive probably. So we're going to go back into the UAV AB demo. Oh, now that's loaded. OK, so this is running with UAV barriers always happening. This is emulating the 11 style synchronization. Notice the frame rate. I think we're sitting at about 40, yeah, 49, almost 50. The average is creeping up. I'll look at the one below it. And now we're going to switch to the optimal UAV pattern. And you can see we've jumped up actually to 60 FPS. I think we're getting a little cropping on the left. So that's about 60 FPS. So we've seen an increase of about 10 FPS, 20%. As you saw Ben was playing, that was live. So yeah, in summary, same main points we talked about last year, but dramatically improved. Greatly decreased CPU overhead, improved scalability across cores. What's new and awesome is we actually get an increase in GPU performance. So if your game was GPU limited, there's still a reason to move to 12 because you'll get more out of your GPU. Further, we've added new GPU capabilities in the rendering pipeline, and ultimately, all these together are giving you, the developer, greater control to achieve what you want in your game in terms of realism and gameplay. So that's it. Thank you. Previous talks, I'm going to advance past this fast, but if some things were fast, go watch these talks. And last, these are all our resources at this GDC. So go to see the expo hall, join early access. We have 2 more talks, tools, and then power performance on Friday. Tools is tomorrow, I think, around 11-ish, 10. And then there are several talks by hardware partners. I'll be doing a small bit in the AMD 12 talk tomorrow. I'll talk more about the memory model, how you allocate resources and manage resources on the GPU.